Hello, welcome to the video solution, or one of, for assignment 25 from the STEP support program. I'll be taking you through the STEP question from this. I recommend that you try the STEP question properly before you look at the solution. And if you've already completed the solution yourself, this can still be helpful because I might give sort of motivation of things that maybe you didn't think of, or else just better reasons to think of the things that you did think of, or whatever. If you haven't quite managed the question, that's totally fine. Just watch along, and then whenever you get to a point where you think you might be able to finish it, or I give you an idea where you haven't had it before, stop and try and finish it. That's really the best way to get things out of this. That's sort of the same philosophy you should be applying to hints and solutions and everything. Also, if you'd like, there are the warm-up and preparation questions before, which are usually quite helpful. In this case, the one in particular certainly helps a little bit. Okay, so without further ado, let's get in. I'm just going to say one more thing, in that this is the sort of step question that can look quite intimidating. You get some pretty nasty integrals and everything. And the second bit especially, there's no hints or anything, it's just do it. But actually, you don't have to be that sort of tricky or clever or anything. It's just, you have to be step savvy. Okay, so it's the sort of thing, if you've done a lot of practice of this type of question, you would probably think of the right things to try quite early on. Okay, so the first part looks a bit like an A-level question. Here's a substitution, here's an integral, find the answer. Okay, maybe it's going to be a lot worse than that, but I've got no better ideas. So let's just go in, blindfolds on, and see what happens. Okay, so the substitution itself is actually quite simple. It's just like a linear substitution. So we're just going to get a minus 1, like d theta is minus d phi, whatever, if you want to think of it like that. And then I'm just going to go straight into the integral because it's not that complicated. Okay, so first of all, it's often a good idea in these things to name, the big thing you're aiming for. Just give it a name. Okay, I'm going to call it I1. Okay, so I1 is equal to that thing. So doing our substitution. Now, by the way, obviously in the video solution, I'm not going to give my full how I would write it out and everything. I would say, doing the substitution, find that E1 or I1 is equal to this thing. I would give lots of justification. I'm going to speak most of the justification. Okay, so doing my substitution, I find that when theta is 0, phi is pi over 4. And when theta is pi over 4, phi is 0. Okay, so the limits have just been swapped. I already said that we're going to get a minus sign from the substitution, so I'm just going to put that here. It looks like a weird arrow. A minus sign here, and then we've got our actual integral. 1 plus tan of theta, which is the same thing as pi over 4 minus phi. Okay, fine. Okay, so, we don't look much better off, let's be honest, but there must be something to this substitution because they wouldn't just be that mean. There is something we can do, which we couldn't really do with the tan theta, and that's sort of rearrange this. Okay, 2 alarm bells should be going off. First of all, addition subtraction formula for trigonometric functions. We have that in our back pocket. Second of all, tan of pi over 4 is a lovely thing, it's 1. We should know that. Again, another sort of quite a high-pitched bell should be ringing off there. Okay, so I'm just going to go straight to the substitution, or straight to the substitution into the formula, the addition subtraction formula. On the numerator, we're going to get tan of pi over 4, which is 1. It takes the sign, so it's minus tan of the second thing, tan of phi. Okay, and on the bottom we're going to get 1, and it's the opposite sign, plus, and then it's going to be the product of this and this, or the tan, product of the tans. So it's tan of pi over 4, which is 1, times tan of phi. Okay, good. So that's this, and now I've got 1 plus this. Again, I'm just going to close my eyes and just do the most obvious manipulation. Okay, so that's 1 plus this is equal to, okay, so I'm just going to do this, equal to ln of 1 plus tan theta, or tan phi, sorry, 1 plus tan phi plus 1 minus tan phi, all over 1 plus tan phi. Okay, lovely. The tan ph's cancel. And now I've got 2 over 1 plus tan phi. So going straight back into our integral, I'm just going to stay kneeling, easy. We've got I1 is equal to, now we've got switch limits to original I1, and I've got a minus sign, so we can just sort of cancel those if you like. I'm going to go back to my original limits and lose the minus sign. I think there's a step question on like why you can do that properly and everything. You should be comfortable with that, but think about it if you're not. And then we've got ln of, now we found it was 2 over 1 plus tan phi. Standard A-level manipulations with ln, we've got a ln 2 minus ln, well, the denominator was tan phi. Okay, now, here is where you sort of realise, this is why it all worked. Okay, because this in the integral is exactly our original I1. Okay, so I'm just going to write this one more time. That's 0 to pi over 4 of ln 2 dphi minus I1. Okay, so now we've got I1 is equal to something minus I1, i.e. 2I1 is equal to that something. 0 to pi over 4 ln 2. Ln 2 is just a number, so this is just the area of that rectangle, which is equal to pi over 4 ln 2, i.e. I1 is equal to pi over 8 ln 2 as required. Lovely. Now, unfortunately, I am not technologically adept enough to figure out how to video myself in bits and then edit the thing. So I'm just going to do it all in one go, much to the detriment of my voice. As you can tell, I've got a cold. Currently trying not to choke on a strepsil. So let's just hope I don't make any mistakes, because then I'm just going to have to do it all again. Okay, so now the second part looks quite intimidating. Perhaps if you've not done much step, or even if you have, it's just evaluate and then some absolutely horrendous looking integrals. Or what would be horrendous if we hadn't just done what we've just done. So evaluate. Now the first one is, I think, 0 to 1 of ln of 1 plus x all over 1 plus x squared dx. And then there's another one, but we'll do that after. Okay, so yeah, as I said, if that just came up and said hello in the street, you'd jump out of your skin because it looks awful. But we've just done something that had, it was a definite integral, and it had a ln 1 plus something in it, and we got a sort of relatively nice answer out of it. So, in the true spirit of step, what we're going to try and do is jiggle about this, and either get to a position where we can do our previous calculation, like maybe a similar substitution, like, I don't know, 1 minus x, or pi over 4 minus x, or something like this, or, and get to, a similar answer, or we'll just directly get this into a position where it looks very like our previous integral I1, and we'll be sitting pretty, because we already know what I1 is. It's pi over 8 times ln 2. Okay, so it's about being step savvy. You've got to aim for what you already know, okay, for what they've given you earlier on. So, in the interest of being step savvy and in saving time, I'm going to try the very first thing that pops into my brain, which is, before I had a tan phi there, or a tan theta or whatever, and now I've only got an x, so I'm just going to put x equals tan theta and see what I get. Okay, maybe I'll get nowhere and I'll have to start again, but it's good first place to start. Okay, so sub x equals tan theta. Okay, so that means that I'm going to get dx by d theta is equal to sec squared theta. Now if I call this I2, okay, just for the sake of being clear. No, it's not quite clear on the video, but it should be okay. Now, so then I2 is equal to, no. Actually, it's going to turn out, well, we're about to find out that this x equals tan theta, which was a pretty sort of like foolproof, just see what happens type of substitution, it's actually going to work out pretty nicely because when x is 0, we get theta 0, and when x is 1, we get theta pi over 4. Okay, not worrying too much about like domains of tan and like, you know, subbing into 1, because it's periodic. So we get nice limits, and we're now looking pretty happy because this is exactly what we had before. And then on the top we've got ln 1 plus tan theta now, because that's what x is. On the bottom we've got 1 plus tan squared of theta, because that's 1 plus x squared. And then we've got to remember our sec squared theta times sec squared theta d theta. And now we're looking really good because 1 plus tan squared theta is sec squared theta. That should be like completely, you know, A level. You just think of that. Okay, there we go. Lovely. And now we've got the integral from 0 to pi over 4 of that thing, d theta, which is exactly what I1 was. So I2 is equal to I1, which was pi over 8 ln 2. Lovely. Okay, so, I mean, that thing looked absolutely, you know, stuff and nightmares, but it was really quite easy. Okay, so this gives us a little bit of momentum going into the last part. And we'll just try the same thing again. Well, not the same thing again, sorry, but the same philosophy again. Aim for what we had before, or aim to sort of emulate what we had before. So this time it's evaluate the integral from 0 to pi over 2, I think, of ln of, I think it's 1 plus sine, yep, 1 plus sine x all over 1 plus cos x. Stretch, so update, I haven't choked, good. Okay, so now, this looks perhaps a little bit more awkward. There's no sort of blindingly obvious thing to try, like x equals tan theta. I'm not saying it should have been blindingly obvious to you, but it's sort of like, I've got no better ideas, let's just try that. Okay. Here, maybe you'll think of something else if you've already done the preparation question. But again, I'm going to sort of fall into, I've got no better ideas, I'm just going to try something. And the thing is, I'm probably going to want a pi over 4 here. Maybe not, maybe it's going to be something different, but it's a good first thing to aim for. So, in the interest of getting a pi over 4 here, I'm going to let x be twice something, and then that's going to at least fix my limits for now. Okay, so my first thing to try is sub x equals 2v. Okay, now let's call this I3, because 3 comes after 2. And then we're going to go straight into substitution. So I3 is equal to, now we've just gerrymandered the limits into being correct, and then we're going to get ln of 1 plus sine 2v over 1 plus cos 2v. Now we can't forget our dx by dv being 2 thing, so that's times 2. I'm just going to, that's a little dot for times 2 dv. Okay, now here we're sort of like, oh, maybe we haven't done anything correct yet, or haven't done anything useful, like it's just as bad, possibly even worse. But at least our limits are correct. So, sorry. Now is a good time to sort of watch out. This 1 plus sine 2v, it's a thing to sort of just like look for, because as you'll see in a second, you can get it into quite a nice form. Now, I didn't actually think of that when I was coming to it, even though I should have. But it's reassuring because that means you don't have to like know this magic thing about, it's not magic, you don't have to know this like handy little trick about 1 plus sine 2v, you know, to do the question. Basically, once again, I was like, I've got no better ideas, let's just, you know, change the double angle formulas into single angle formulas. That's bad, I think. Let's just apply double angle formulas and sort of see what happens. So, to this thing, that's an awful bracket, but whatever. We've got 1 plus, now sine 2v is the same thing as 2 sine v cos v. And on the bottom, Now, I've got a choice of 3 different double angle formulas for cos at my disposal. I'm going to pick the one that's 2 cos squared v minus 1, just because then the minus 1 will cancel with the plus 1. So that gets me a 2 cos squared v, minus 1 and 1 plus, so they cancel. So I'm going to have this. Now, looking okay. I mean, there's a tan here, but a sec squared here, so it's maybe not great. But then you think, oh, 2 sine v cos v looks a bit like the middle term in sort of an expanded square of like a sort of an a plus b squared. You get an a squared plus 2ab plus b squared. So, and even better, it's just here, I can write 1 as cos squared v plus sine squared v. Okay, so I'm going to do this. Cos squared v plus sine squared v. That's just one. That should always be like, if you ever got a 1 floating about in these trigonometric sort of manipulations, think about what happens if you turn it into cos squared v plus sine squared v. It's shockingly useful. And plus 2 sine v cos v, all over 2 cos squared v. Okay, what happens? Okay, well this is just it's just a square. Okay, so we get cos v plus sine v all squared all over 2 cos squared v, i.e. a half times, and then we've got 1 fraction all squared, cos v plus sine v over cos v. Excellent. In fact, even better than excellent, because this is exactly 1 plus tan v. Okay, so now we're looking pretty good. Okay, so let's go straight back into our integral. I3 is equal to 0 to the power of 4, after we changed x equals to 2b, ln of, or twice, I'm just going to put 2 here, 2 times the ln of half, now we've just discovered this 1 plus tan v, all squared. Okay, now we can do our standard ln manipulations, and okay, so this next step requires no brain. Okay, it's just 0 to the power of 4 of 2 ln a half plus 2 ln. Oh, okay. Ignore my last 10 seconds of talking. I've got a 2 ln a half here, and then we're going to add it to sort of the 2 times the ln of this. But then the square comes out, so we're going to get a 4 here. 4 ln of 1 plus tan v. Sorry, I was doing that in my head as I was explaining it, and it didn't really work. That's correct now. Just think about, like, if I've confused you with my explanation, I'm really sorry. Just shut me up for a minute. Go from here to here on your own. It's totally doable. Okay, sorry about that. Okay, so now we're looking really, really good. Okay, because this is exactly our original integral I1. Okay, and this is going to be quite easy to evaluate. Okay, so I'm just going to get that. We've got 0 to the power of 4 of 2 ln a half, i.e. minus 2 ln 2 dv plus 4 times I1. Okay. Now, this is again, it's just going to be the area of the rectangle, signed area of the rectangle. But yeah. Okay, so it's now pi over 4 times minus 2 ln 2, i.e. minus pi over 2 ln 2. And I1 was pi over 8 times ln 2, so 4 of those would be pi over 2 ln 2. Alright, okay, so plus minus equals 0. And that's our answer. Okay, so that's the step question done. Now, if you've done this on one, I was quite surprised when I did this on paper. It only took me one side of paper. Obviously, if you sort of made mistakes or whatever, it's going to take longer. But if you sort of just do the foolproof thing each time, you're going to be able to actually get this out quite quickly, even though it's potentially quite an intimidating looking question to start with. I know when I was taking STEP, this might be the sort of question that I'd be like, oh, jeepers. I'll either make so many algebraic mistakes or I won't come up with the clever substitution, whatever. But sometimes these things are a lot more tackleable than they look. Yeah, I think the main takeaway from the STEP question is just be step savvy, okay? At no point there were we particularly clever. I think the trickiest thing was this little step here, going to the perfect square, the cos v plus sine b all squared thing. This would have been made easier if you'd done the preparation question, but it's totally doable without having done that, especially if you remember your little handy thing about 1 plus sine 2b. But if the hardest thing about a step question is just a little trick like this, then that's a pretty good place to be in, okay? Yeah, I don't think I've got anything else to say. Great. Good luck with all your preparations. Bye.